All right, hello everyone. Let's start in on chapter 4 material. This chapter we're going to be dealing with the simplest functional group that we've talked about thus far, which is just the alkanes. Specifically, we're going to work on alkane nomenclature in these next few lectures, and so it's sort of broken down in this step-by-step process. The goal of this video is going to be to find the parent chain, and of course I'll explain what that means. First of all, let's just remember what we're talking about when we're talking about the alkane functional group. These are hydrocarbons, compounds that consist only of hydrogen and carbon. More specifically, when we're talking about alkanes, we're talking about compounds that do not contain any pi bonds. Okay, and for alkanes, they also don't contain any rings. They are what are called saturated hydrocarbons. These all have the same formula, CnH2n plus 2. We are going to talk about cyclic alkanes in this compound, or in this set of lectures in this chapter. But for this particular lecture, we're focusing just on alkanes or saturated hydrocarbons. Okay, you can spot an alkane in terms of the nomenclature by the ending on the name. They always end in ANE. That's the signature suffix for an alkane. And we're going to learn how we get these names. They correspond to the number of carbons. Prop is 3 carbons, but is 4, pent is 5. And so we'll see a chart that sort of lists all those relationships, okay? Again, remember when we're talking about alkanes, we're not talking about anything that has any pi bonds, right? Remember, those were alkenes or alkynes. Those are going to be saved for another chapter. So when we're talking about naming alkanes, first of all, some chemicals have existed for such a long period of time that they have what's called a common name that just sticks around. So morphine, for example, that's the common name of a drug, a painkiller that I'm sure we've all heard of. That's what this big ugly molecule right here is called. It also would have a systematic name, which is what we're going to be learning about today, but it's just not widely used. It's been around for so long that people always refer to it by their common name. Urea is another good example. Urea is actually famous in the world of organic chemistry because it was the first molecule that was both isolated from a human being, it can be found in urine, but also synthesized in the lab. So it was an important proof of concept that actually, yes, even though living beings are obviously very special and complicated, they are still made up of the same chemistry building blocks the rest of the world is made up of. But yeah, so these are what are called the common names. What we're going to be focusing on are what are called the UPAC naming system. So this is a systematic way, given any molecule, you can break it down and figure out what the name is. And this has a few steps. The first step is to find and name the parent chain. That's really what this video is focused on. Okay, so here's an example molecule down here. This is this big ugly hydrocarbon, as you can see. It consists of a parent portion. And again, this video is going to be all about finding and naming that parent chain, as well as everything coming off the parent chain are what are called substituents. So that's what the next video will be about labeling substituents. Then the last step, when you go to put it all together, you got to number the parent chain and then construct an alphabetical order. So again, we're breaking these tasks down into different segments, and this video in particular is just going to focus on the first part there, finding and naming the parent chain. So what do I mean by finding the parent chain? So the parent chain is the longest consecutive chain of carbons. So given a molecule like this one here, we're going to go through and find the longest consecutive chain of carbons. Okay, so at first, you'll get pretty good at this once you practice, but at first it's just kind of a guess and check thing. You're going to start at one end and start numbering. 1, 2, 3, 4, 5, 6. Okay, is there one longer that I can find? I'll use a different color. 1, 2, 3, 4, 5, 6, 7, 8. All right, so that's already better than my first one. So if you went through and did all these different possibilities, you would find that 1, 2, 3, 4, 5, 6, 7, 8, 9. This segment right here is the longest consecutive chain of carbons. Okay, notice that I can't count You know, I can't go 1, 2, 3, oops, 4, 5, 6, and then jump back over here, 7, 8, because that wouldn't be continuous, right? So your goal is to find the longest continuous set of carbon atoms in a molecule. So again, our parent chain for this one would contain 9 atoms, okay? These guys off the side of your parent chain, these are the substituents. So again, we'll worry about labeling them next video. In this particular video, we're only focused on this parent chain. Again, the longest consecutive chain of carbons. Every once in a while, you'll get a molecule that you can label 2 different ways, you can number 2 different ways, and still come up with the same number of carbons in that longest chain. So this is a good example here. All right, so I have 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. So which one of these 2 numberings of my parent chain is correct? Or which one of these 2 contiguous segments of carbons are my actual parent chain? In this case, when you have a tie like this, you're going to choose the parent chain to be the one that has the most substituents. Okay, so on the example on my left, this has 1, 2, 3 substituents, right? Those are all carbon atoms that are lying outside of the parent chain, making them substituents. And on the right molecule, I have 1, 2 substituents. All right, so that's why the left is going to be considered to be the more correct parent chain, because it has the most substituents. On this side, I have 3 versus 2 on this side. Okay, so that's only when there's a tie that you're going to have to worry about that. All right, so now how do we name our parent chain? So the number of carbons, you know, there's a 1-to-1 correspondence between the number of carbons in the parent chain and the name of that parent chain, okay? So let's go through. 1 carbon, that's going to be the prefix meth, or the parent chain will be methane. 2 is eth, or that parent chain would be ethane. Again, the ane because it's an alkane. 3 is prop, as in propane would be the name of that parent chain. 4 is bute, as in butane would be the name of that parent chain. And then from there, it kind of makes sense based on, you know, what you would have had from a geometry class, for example. 5 is pent, 6 is hept, 6 is hex, 7 is hept, 8 is oct, 9 is non, 10 is dec. This side is what I expect you to have memorized for the exam, 1 through 10. Okay, anything else, I'll give you the chart or something like that. But you have to have 1 through 10 memorized. And again, specifically, I think these first 4 are the hardest ones. It's good to just get them down: meth, eth, prop, bute. Okay, so have that sort of down in your head. That's 1, 2, 3, 4. From then, it sort of corresponds to what we learned in geometry. 5 is pent, 6 is hex, 7 hept, et cetera, okay? So again, the number of carbons in your parent chain corresponds uniquely to the name of that parent chain. So let's go through these examples right here. Actually, this is a good place for you to pause and take a second and see if you can't name the parent chain all on your own, and then play it back as I go through them. So for this top one here, again, the longest contiguous set of carbons is going to be 1, 2, 3, 4, 5 carbons long. And so my parent chain here is a pentane. Has 1 substituent. Again, we don't know how to name this substituent yet. We'll do that next video. Now we're only focusing on this parent chain portion. Okay, what about the molecule below? 1, 2, 3, 4, 5, 6, 7. 7 carbons makes this a heptane, is my parent chain. So this is a heptane. And I just want to note that if I had not numbered that, if, you know, instead of having this carbon be 7, I could have had this carbon be 7 and it would have been perfectly equivalent. It might take till when we get to this next step to see why that is, but in this case, because there are no more or less substituents based on those 2 numbering schemes, either of them you can choose. Okay, so this is how we're going to name our parent chain. The last thing I want to talk about, because we are going to be talking about cyclic alkanes as well in this chapter, is how we name cyclic alkanes, and those will all have the prefix cyclo at the beginning of the parent chain name. So this is 1, 2, 3 carbons. Do we remember what prefix is 3? So that would be prop or propane. So this is cyclopropane. Likewise, 1, 2, 3, 4. Do we remember the prefix for 4 carbons? That will be bute or cyclobutane. And lastly, we have 1, 2, 3, 4, 5. So that will be cyclopentane. You can also have cyclohexane, cycloheptane, cyclooctane, et cetera, et cetera. The whole idea being you're just going to stick cyclo in front of as a prefix to that parent chain name. Okay, so go ahead and practice naming these parent chains, and then we can jump on to actually naming the substituents.